So we're in section 15.3 today. We're going to talk about conservative fields and independence of path and the fundamental theorem of line integrals. Thursday. And the result that we get to today is a really cool result that's really very powerful. So the first thing, just to kind of motivate what we're doing, I want to think about either a charged particle or a planet or something, and we have another mass or another charged particle out here. Now, in that situation, our force, let's say it's an attractive force. So our force is always directed from the one object to the other object. So if and we're talking about the amount of work done by this force that's between these two objects. If I move radially this way, how much work is done by the force? Zero. No work, right? Because the force is only directed between the two. And then if I go this way, let's say we're starting here at point A and go to point B. So no work done here, and then I move this way a little bit. So the work done here is the force times this little distance that I move towards the other object, right? Now what if I move radially again? How much work is done there? None? And then I go, and I'm going to draw little arrows here. So we're moving on this piecewise smooth path. And now I go this way. The work done by the force is proportional to this distance that I've moved towards it, right? I move radially again. How much work? Zero. And I move this way. So the force again is proportional to the distance that I've traveled. And I'm going to keep doing this until finally I get to the other object. So what's the total distance that this force has actually done some work over? From A to B. So the distance, the work is only proportional to this distance, and we'll call it R. It doesn't matter if I kept going around. I could go around and around as much as I wanted to. The only thing the only time that this force does any work on the particle is when it's moving directly towards the other object. So the work only depends on the distance from A to B. It doesn't depend on how far I move around radially. I could go around and around as much as I wanted. It only depends on the distance from A to B. So that's going to be our kind of jumping off point. All right. It turns out that for any conservative field, and we talked about conservative fields right at the beginning of the unit, for any conservative field, the integral over a path, the line integral over our path, only depends on the initial and the final points. So for conservative fields, that's a special property of conservative fields. That's why we spent some time talking about them. So for a conservative field, the line integral only depends on the initial point and the final point. So let's talk about conservative fields and kind of develop what we're going to do today. So for conservative fields, line integrals only depend on the initial and final point. So let's take a look at why that's the case. Remember that for a conservative field, we can say that the vector field is the gradient of some scalar function. And f is the potential function. So this leads us. We're going to state our fundamental theorem of line integrals, and then we'll show why it works. So we have a conservative field, so that means that our field is the gradient of some potential function. So the fundamental theorem of line integrals. And we have a couple of conditions that we have a path. And our path is defined by some parametric equation. And I'm going to say R of t. And that's x of ti plus y of tj. And we'll talk about it in the plane for now. The extension to space is it's very simple. We just add another component. And we're going from a less than or equal to t less than or equal to b. And we're in an open region. If our field is mi plus nj, and if this field is conservative, then our line integral along C of f dot dr, which we talked about before, and that's the same as the line integral of f dot r prime. And this is, because this is a conservative field, we have a potential function. This equals f of x of b, y of b, minus f of x of a, y of a. And a couple more conditions. M and n are continuous. And we said that f of our field, our vector field, is the gradient of our scalar potential. And finally, C, our path, C is piecewise smooth. So let's think about what this is telling us for a second. If we have a conservative field, then our line integral only depends on the final point and the initial point. We can evaluate our potential function at the final point, subtract that potential function at our initial point, and that gives us our line integral. So this avoids having to evaluate. If we have a conservative field, it avoids having to evaluate difficult line integrals if we can find a potential function. And it allows us to not worry about the path. So we'll talk a little bit more about that in just a second, but this is a very powerful tool if we have a conservative field. All we have to worry about is the potential function at the final position and the potential function at the initial position. So this relates back to our fundamental theorem from single variable calculus, where to evaluate an integral, we just needed the antiderivative at the final point and the antiderivative at the initial point. We didn't worry about what was happening in between. All we needed to know was what was happening at the end point. So this gives us a very, very powerful tool, and it's going to lead us to a lot of different things. So let's look at why this works. Why, if our vector field is conservative, that our line integral only depends on the initial and final position. So we're going to say f is conservative. We're going to be given f is conservative. So our vector field is the gradient of a potential function. And that means that f equals, we're going to write out the components of our potential function. F is the partial of our potential with respect to x, is our I component, plus the partial of our potential function with respect to y, and that gives us our j component. That's what the gradient of our potential function is. So our line integral of f dot dr, which we said we evaluate by doing f dot r prime dt. And I'm going to plug this in for f and plug in an expression for r prime. And we're saying that r is just x of ti plus y of tj. That's our parameterized curve. So f dot r prime, the line integral of f dot r prime, we have the integral from a to b of df dx, dx dt, plus df dy, dy dt. This is our dot product with this and r prime. By the chain rule, this is the integral, our line integral of f dot dr equals the integral from a to b of d dt of our potential function. And let me write this out. F of x of t, y of t, dt. And our fundamental theorem, our original fundamental theorem of calculus, what does our fundamental theorem of calculus tell us the integral of a derivative is? Just the function, right? So this is just f of x at b, y at b, minus f of x at a and y at a. And we're done. So because f is a conservative field, it's the gradient of a scalar function, and that allows us to express it as the scalar function evaluated at the final position minus the scalar function evaluated at the initial position. Now what happens, before going, does anyone have any questions about this? All right. So what happens if a equals b?
0.
Our line integral is 0. So this is another important fact. If a equals b, our line integral equals 0 if f is conservative. If a equals b, what kind of curve, what kind of line integral do we have? Or a circle or some kind of closed curve. So if a equals b, c is a closed curve. So if we have a conservative field and we take the line integral over a closed curve, that line integral is always 0. So there's another important little fact that we have. If we have a closed curve and we're taking the line integral of a conservative field over a closed curve, our line integral is going to be 0. And so what this implies, and the power of this idea, is that f is continuous in some region. The line integral of our conservative field along any curve from one fixed point to another has the same value regardless of what path we take. So what we did back here in our little proof, we just said r is some parameterization of our curve. And this is an arbitrary parameterization, and our line integral was just f evaluated at b minus f evaluated at a. So our line integral, no matter what this curve is, our line integral is going to have the same value. So if we have a line integral from along this curve of a conservative field, it's the same as the line integral along this curve. It's the same integral as the line integral along this curve. And this one's not simple because I made a little. Or it's the line integral from here to here. It doesn't matter what the path is, and it only depends on the initial and the final position. So if we have a conservative field, we can take the line integral along any path and get the same result. So if we have some ugly, complicated path with a really difficult parameterization, and we know our field is conservative, we can just take the line integral along a straight line from A to B. Much easier. So I'm going to state that as a theorem. If f is conservative, if our vector field is conservative, on an open connected region, then the line integral of f dot dr is independent of path and I'm going to say if, and I'm going to put another f there. That second f means if and only if. If and only if f is conservative on an open connected region, then f dot dr is independent of path. And a connected region means just what you would think it means. Here's our region from A to B. So this is connected. This is R. This region is not connected. So we have to make sure that we're talking about a connected region. And when we start talking, when we go a little further, we'll run into some places where we have to make some adjustments for connected and not connected. So if and only if we have a conservative field, so if and only if means it works both ways. If and only if f is conservative, then our line integral of f dot dr is independent of path. If our line integral is independent of path, that implies that our field is conservative. Questions on that? All right, so now for conservative fields, we have three options. We have three options for evaluating a line integral. And these are equivalent conditions. They give us the equivalent, they're equivalent procedures. So for conservative fields, to evaluate a line integral, our first option is to evaluate it as is. We know how to evaluate line integrals on vector fields. We have the tools to do this already. We know how to evaluate line integrals. This can sometimes be difficult and tedious depending on our field and depending on our path. So depending on our parameterization, depending on our field, this can be difficult. Our second option is to integrate the components of f to find our potential function. And then we just evaluate the potential function at the final and the initial points. And we're going to use the fundamental theorem. So if the problem asks you, and there are several problems in your homework that'll say, use the fundamental theorem of line integrals to evaluate this line integral, this second option is what they're asking you to do. Integrate the components of f to find your potential function. And we did some of these in a previous section where we integrate the components to find our scalar, or to find our potential function. So when the problem asks you to use the fundamental theorem of line integrals, this second option is what they're asking you to do. Our third option is to pick any easier path. And evaluate the line integral along that path. So we can pick any path. If f is conservative, if our vector field is conservative, pick any path and evaluate the line integral along that path. Pick the easiest path that you can think of. If we can do a path along the x-axis, then x is 0. And everywhere you see an x in your line integral, you can plug in a 0. And dx is going to be 0. So if we have it expressed as m dx plus n dy, and we're integrating that, all the x's are going to be 0, and dx is going to be 0. So that gets rid of a whole bunch of stuff that you have to integrate. So that makes it a lot easier. If we have some complicated path, we can pick the easiest path that we can imagine to evaluate the line integral, and it makes our work a lot easier. These are equivalent conditions, equivalent processes when we have a conservative field. Questions so far? Now let's remember how we figure out if we have a conservative field. If we have our function in our field in the plane, what was our test for conservative fields in the plane? We remember?
Path of x, y equals f of y x.
Yes, I think that's one way of saying what we did, and the way we stated it is dm dy equals dn dx. If we have a field in space, what was our test for a conservative field in space? Del cross f equals 0. So from here on out, what I would recommend when you have a line integral to evaluate, unless it gives you some kind of conditions, if you're evaluating a line integral of a vector field, see if that field is conservative. See if you can simplify your work. That should be your first test if you're evaluating the line integral of a vector field. Is f conservative? If it is, then you can simplify your work. And do you remember what we called del cross f? The curl. So that was our test for conservative fields in space. All right, any questions? All right, let's look at one quick example. In your book, on page 1086, if you don't have a book, share a book with somebody. 1086, we're looking at number 16. So number 16 gives us a line integral over a bunch of different paths. So our vector field, F is, or we're looking at the line integral along these various paths of 3x minus 3y, or 2x minus 3y, plus 1 dx, minus 3x plus y minus 5, dy. So we're looking at this line integral. And we want to evaluate this along various paths. So the first one is piecewise smooth. The second one is a half circle. The third one is a half circle, and we're evaluating it. Or number D is a half circle, and we're evaluating all around the half circle. And C, we're evaluating it along that curve y equals e to the x. But now that we know about the fundamental theorem of line integrals, we're going to say, let's check if this field is conservative. So I'm going to rewrite this. I'm going to say that my vector field is, the notation we've been using is mi plus nj. So that equals, so m equals 2x minus 3y plus 1. And n equals minus 3x plus y minus 5. So we were going to see if this is conservative. dm dy is what? Dm dy is negative 3. And dn dx equals negative 3. So our field is conservative. So right away, what do we know about the line integral of A and C? They're 0 because we have a closed path. So A and C?
Wait, you mean A and D?
Or I'm sorry, A and D, yes. A and D. A and D equals 0 because they're closed paths. We didn't have to do anything. And from, if we look at, let's look at, rather than looking at C, let's look at B, the line integral along that path. So we would parameterize that curve probably as some circular function with sines and cosines and put limits on theta. But since f is conservative, we can pick any path. So let's pick that vertical line from -1 to 1. So let's pick, since f is conservative, we can pick any path. Let's let r of t, and we're looking at, sorry, this is B. Let's let r of t equal tj. So we're just going straight up the y-axis for -1 less than t less than 1, less than or equal to 1. So for our parameterization, y equals t, dy equals dt, x equals 0, and dx equals 0. So for our integrals, since dx is 0, this whole first term disappears. And for our second term, x is 0, so this part disappears. So all we're looking at is the integral, and I'm just going to write it in shorthand. The integral along C is the integral from -1 to 1 of minus t minus 5 dt. X is 0, y is t, and dy is dt. for the second integral. And we evaluate that on 1 to 1, and we end up with 10. Very easy integral to evaluate. We didn't have to worry about any crazy parameterization. We picked the easiest one we could think of, the easiest path we could think of.
What is this, like, what is 10 telling us?
10 tells us the sum of the tangential components of f along the curve, along any of those curves. Okay? All right, questions? This is a 5. 5 came from here. All right, homework. Just a straight line from the initial point to the final point. Yep. And
How do you know what the initial point is?
it gives you 0. For C, it says the initial point is 0, 1.
Oh, yeah. I was looking at A, so then I was like,
All right, there you go.